Hello, Math Humans. We're going to do 5.3a today. We're going to be solving trig equations. So our objectives are that we're going to solve trig equations using algebra, math, and some trig identities. So the hint that I will give you is that most of these problems are going to involve our special right triangles. Okay, and we've been talking about that now for about a chapter and a half. So I'm just going to redraw those just because I can, right? So this is a 30, 60, 90 right triangle. The way that I teach it, opposite the 30 is a 1, opposite the 60 is a radical 3, and the radius is 2. And then I can develop all of my trig ratios given that information. And then in a 45, 90, remember that the legs are congruent. It's 1, 1, radical 2. So based off of those two triangles, I can develop everything that I need. So now let's just jump right in with our first example. And I think I say that every video, so I'll apologize now. I'm sorry. So we're going to solve, and we want to do exact. Remember that exact means you should be showing your work and not using your grapher. We're going to be given that the sine of x is equal to a half. So we're going to start off nice and polite. I'm trying to find x, so this says what angle has a sine ratio. So technically I would get x is equal to the arc sine of a half. But what I'm going to do is I'm just going to draw two triangles. Sine is here, so this is 1 and 2, so that means this is radical 3. Sine is also positive in the second quadrant, and this is a negative radical 3. This is pi over 6, then this is going to be 5 pi over 6. So just as a reminder, let me show you how I found 5 pi over 6. Typically what I do is I alternate or I bounce off of my horizontal axis. So I'm going to go all the way to pi. So there's my pi, and I'm going to back up the same angle, which is pi over 6. I need to add the two fractions together, so I multiply by 6 over 6, and there's my 5 pi over 6. Instead of trying to memorize, if you add and subtract from your horizontal axis, this is a very easy process. So then I would report x is equal to pi over 6 and 5 pi over 6. Okay, example 2. Again, we're going to want to solve, and the majority of the time we're going to be looking for exact, which means you need to do it by hand, no grapher. In this one, we're going to be given the sine of x plus radical 2 minus the sine of x, and we want to solve in the interval from 0 to 2 pi. 2 pi is not included because we want one rotation. So what I'm going to do first, this is equals a negative sine x. I started looking at that. There's no way I can solve that. So I'm going to bring this sign over here. So I'm going to get the sine of x plus the sine of x equals, take this guy to that side, negative radical 2. So I get 2 sine of x is a negative radical 2. Sine of x is a negative radical 2 over 2. Now, one of the things that I talk a lot about in trig work is unrationalizing. So this is also a negative 1 over radical 2 because I think this is easier to manage. So now technically I'm solving for x. Sine is negative here and here. Okay, so this is going to be a negative 1. This is radical 2. So this is 4 pi over 4, 5 pi over 4. And then this is going to be all the way back to the axis, 8 pi over 4 minus 1. This is 7 pi over 4. So x is going to equal 5 pi over 4 and 7 pi over 4. Next example, example number 3. It says solve. Again, we're going to have that lovely word exact. And we're going to solve from 0 to 2 pi. So we want one complete rotation. And in this one, I'm going to be given 3 tangent squared x minus 1 is equal to 0. So they're just simple equations. So I'm going to take the 1 to the other side. So 3 tangent squared x equals 1. Divide by 3. The tangent squared of x is 1/3. Take the square root of both sides, and I get the tangent of x is plus or minus, don't forget your plus or minus, 1 over radical 3. So in this one, tangent is positive in the first quadrant and the third quadrant. Tangent is y over x, right? So that means this is 1 radical 3, this is 2, this is pi over 6, and this is 6 pi over 6, 7 pi over 6. So I'm going to write here x is equal to pi over 6 and 7 pi over 6. Tangent is negative in the second and the fourth quadrants. So again, this is going to be a 1, and this is radical 3, negative. This is where I get the negative. So this is 5 pi over 6. So I'm going to add that to my list of answers. And then this is all the way around would be 12 pi over 6. Back up 1, this would be 11 pi over 6. So with our specials, it's actually really easy to get the solutions that we need. Alrighty, example number 4. I want to solve. We always want to solve from 0 to 2 pi, and we're going to have exact if possible. Okay? Alrighty, so in this one, we're going to be given the cotangent of x times the cosine squared of x is equal to 2 cotangent x. Well, I'm solving a quadratic, so I want everything on the same side. There's my quadratic, so I'm going to get the cotangent of x cosine squared x minus 2 cotangent x equals 0. These guys both have a cotangent in common, so I get the cotangent of x times cosine squared x minus 1 minus 2 equals 0. So now, just with regular quadratics, I have two baby equations, so then I'm going to solve. So the cotangent of x is going to equal 0, and this is cosine squared x equals 2. Okay, so if we think about the cotangent of x, cotangent is cosine over sine. So cotangent is going to be 0 where cosine is 0. So cosine is 0 at x is equal to pi over 2 and 3 pi over 2. If I solve this one, I'm going to get cosine x is equal to plus or minus the square root of 2, which is plus or minus the 1.414. If you'll remember, cosine oscillates between a plus or minus 1, therefore this one is extraneous, EOUS, because it doesn't create a solution, because it's outside of the range for cosine, so then these would be my two solutions. Next example is going to involve some factoring, because we love to factor. So example number 5, it's your favorite F word. I want to solve, and I'm going to have 2 sine squared x plus 3 cosine of x minus 3 equals 0. So before I start, and I want to solve from 0 to 2 pi, I notice that I have sine things and cosine things. So I need to have all the same variable to make the math easier. So I'm going to rewrite sine squared. So I'm going to have 2 times 1 minus cosine squared x plus 3 cosine x minus 3 is 0. Going to distribute 2 minus 2 cosine squared x plus 3 cosine of x minus 3 is 0. I'm going to combine like terms, so I get a negative 2 cosine squared x plus 3 cosine of x minus 1 equals 0. Now, it's really polite if the leading coefficient is positive, so I can divide both sides of the equation by a negative 1. So I get 2 cosine squared x minus 3 cosine of x plus 1 is equal to 0. So this is going to factor to be 2 cosine of x, and then here's my cosine of x. I need a negative 3 in the middle, so that means both of these guys have to be negative, so I'm going to do a negative 1 and a negative 1 equals 0. If I check, this is 2 cosine squared x. This is a negative 2 minus 1 is a negative 3, negative, negative, positive. So when I solve this baby equation, I get the cosine of x is equal to a half, and this baby equation is going to be the cosine of x is 1. I'll do this one first because it's a little bit easier. Cosine is 1 right here, and so x is equal to 0. Cosine is a half. Cosine is positive in the first and fourth quadrants. So if this is 1, this is 2, this would be radical 3. This is pi over 3 and 5 pi over 3. Just to mention this, we're giving one positive rotation, which is why I'm not considering the negative rotation. So my solutions are x is equal to 0, pi over 3, and 5 pi over 3. Alrighty. One more example, and then we're done. So sometimes the wording on our problems gets to be a little bit entertaining. So sometimes we're told to find or solve. We see those words together. Find the solutions from 0 to 2 pi. And that's one positive rotation. And those are the examples that we've been doing. Sometimes you'll see the words that say find all solutions. And when this is the case, you have to think about, I have a periodic function who is going on forever and ever and ever in both directions. So when we have something that says find all solutions, then we have to consider that those values, really crappy drawing by the way, repeat every cycle or something. So you want to make sure that you're paying attention to the directions. Am I doing it in one complete rotation, or am I doing it for all eternity? This one might be x is equal to pi over 2 plus maybe it's pi n. And we'll talk about this more as these types of problems show up. Our last example, example number 6, is still going to be what we've been doing so far from 0 to 2 pi. And I want to find all solutions. The lovely caveat is from 0 to 2 pi because I don't have to think about how often the values repeat. And in this one's going to have a unique algebra step. Plus 1 is equal to the sine of x. So as we look at this, there's really not a lot that I can do because neither of the cosine or the sine are squared. But I can do whatever I want as long as I do it to both sides of the equation. So I'm actually going to square both sides of the equation. On the left-hand side, I'm going to get cosine squared x plus 2 cosine x plus 1. On the right-hand side, I'm going to get sine squared x. But I need to have everything in terms of the same variable, so I'm going to rewrite this as 1 minus cosine squared x. Now everything is in terms of cosine. I'm going to combine like terms because it's a quadratic, so everything needs to be on the same side. So I'm going to get 2 cosine squared x plus 2 cosine x, and then equals 0 because the 1's cancel. Now I'm going to factor out a 2 cosine x, and I get cosine x plus 1 is 0. Now when I set my two baby equations equal to 0 and solve, I get the cosine of x is 0. 0 divided by 2 is 0. And then the cosine of x is a negative 1. Cosine is 0 at pi over 2 and 3 pi over 2. And cosine is a negative 1 at pi. So my solutions would be x is equal to pi over 2, 3 pi over 2, and pi. All right, that's it for today. That was kind of a nice one. I'll see you soon. cursor keeps getting stuck. It's just weird.